So welcome back RCC short note. Today we are going to see the shear design. Okay. We are going to see about in this introduction and next one is design of beam under shear. So first of all, in the introduction part, we are going to see how the shearing stresses happen on a beam. So for example, there was a beam. Let us take a simply supported beam which is subjected to UDL acting throughout the span. This is W kilonewton per running meter, and this is the length. And this is the shear force. The distribution of shear force is something like that, and corresponding, this is the bending moment, parabolic in nature. Okay. The analysis of bending moment will be over in the last two classes, that is working stress method. So we having seen how to analyze with respect to this bending moment, and in limb state method also we having seen. So this is over. Now we are going to say this one, shear design. For make sense you peoples, I'm going to take 3 points where bending moment is 0 and shear stress is maximum. Point number 1. Second point is both will be present, shear force and bending moment. And the third one is there is no shear stress, only the bending moment is acting on a beam. So like that, I'm going to take these 3 points, how the shearing stress is varying. Point number 2, point number 3. So if you take, this is the section number 1, this is the section number 2, section number 2, this is the section number 3. Okay. Now if you magnify this diagram, then I'm going to draw this diagram in 2D. Okay, in 2D. Then so our beam is something like that. This is our beam and our support. This is our support. Okay, and this also our support. Okay, now this is the center line of support. Center line of support. Okay, we know that this maximum shear force is WL by 2, WL by 2. And the maximum shear force, that is a reaction, is this is WL by 2 at the center of the support, WL by 2. And this distance we are taking as the clear span or clear distance. This is the clear sorry, this is the effective distance, L effective length, and inner to inner distance is clear span, LC. Okay, now first of all we have to take the extreme point, that is at a support, how the shear is varying. Okay, how the shear is varying. This is the neutral axis. This is the neutral axis. Now let us take the first point. At the first point, somewhere here, okay, so somewhere here you have to take, then just magnify that point. Generally our idealization to analyze is the cube. So this is the cube. Now how the shearing internal forces are acting. So here the internal force is only shear force. There is no bending moment. Therefore, this is the shear force. Pure shear force is acting. Pure shear force is acting. Pure shear force. So because of this action, this edge and this corner and this corner getting elongated, and this corner getting contracted. That means to go something like that, and this corner getting expanded. Yes or no? So in this direction there was a tensile force which was acting. Therefore the failure is happen along the diagonal. So in this diagonal there was a failure is happen. Okay, so the failure, the stress corresponding to this is sigma 1. We can say sigma 1. So this is the manner the stress is acting. And the plane at which the failure is happened, we are calling it as, this is the major principal plane. Now second point that we are going to take somewhere here, that is a point number 2. Let us take, and now this point is subjected to shear force, not only shear force. This point, second point, is subjected to shear force and bending moment. So bending moment, due to bending moment we are having a bending stress. This is sigma x. Okay, now also if you find out the principal plane, then the principal plane acts at a distance at an angle of theta p, which is equal to 45 degree or 135 degree, right? So that you having seen in the principal stress analysis. Okay, so but anyhow, somewhere this plane the failure is happen. Okay, because of what? Principal stress. This edge getting elongated this direction, this edge is getting elongated this direction. Therefore the tensile force which is acting along this diagonal, because of the effect of Poisson's ratio, this will be contracted. So this diagonal is subjected to compression, this edge is subject to tension. Therefore the failures happen along this diagonal. Okay, and this also a principal plane. And the next point is center. Next one is center. If you take a cube at the center, at the center point there is no shear stress, only we are having a bending moment. So we are having a bending moment. We are having, sorry, this is not a way to represent the shear stress. Bending stress sigma x, only the bending stress is there, there is no shear stress. And here what is a failure plane? This is the failure plane. Okay, now this plane is called it as here principal plane. So this is the principal plane. This is sigma and sigma x. Okay, now from that we understood at near the support the dominated stress is the shear stress, and the shear stress domination gradually decreases from support to the center and gradually increases the effect of the shear force support to the center to the support. Okay, so from that we understood near the support the effect of shear is very high, therefore near the support you have to provide the reinforcement, shear reinforcement. You have to use the shear reinforcement somewhat closer in nature. Shear reinforcement somewhat closer, certain distance, and you can increase the spacing up to center. Then again you have to reduce the spacing closely spaced up to the end. Okay, why we are using this closely spaced at its support? Because the shearing stress is very high. Okay, so that is the thing. Now see, this is the some of the introduction point. Now we are going to see how the shearing stress is resisted. Okay, shearing stress resisted by section. Shear resistance of concrete. Shear resistance of concrete. Okay, how the shearing resistance of concrete is happen. For example, let us take a beam segment. Okay, beam segment. The shearing resistance of concrete is happen in the three ways. So the first way is somewhere here there was a reinforcement. Okay, so the reinforcement also contribute the shearing resistance, and this is called double action. Double action of main reinforcement. RF means reinforcement. Not only this, there was a tensile, there was a interlocking, and there was a frictional resistance, and this quantity is shear resistance due to interlocking of aggregates. And the next one is this one. This quantity is shear resistance due to shear resistance due to uncracked section, uncracked concrete. So this is the cracked portion, this is the uncracked portion. I'm saying this is the double action. Therefore, this quantity is denoted by VC, shear resistance by the uncracked portion, and this quantity is represented by VA, that is shear resistance due to interlocking of aggregate, and the last one is this is VD because of the double action. Therefore, total shear resistance of concrete, which is equal to VC plus VA plus VD. Okay, so this is the shear resistance of concrete. Okay, not only this, the total shear resistance, total shear resistance of section, total shear resistance of section with shear reinforcement, which is equal to VC plus VA plus VD plus shear resisted by shear reinforcement. What is this? This is shear resisted by shear reinforcement. This we can say shear resisted by shear reinforcement. Shear resisted by shear reinforcement. What is the meaning? Shear resisted by shear reinforcement. Not only these three quantity, also the shear resisted by stirrups. This is the shear reinforcement. Okay, so these all are called it as stirrups. Stirrups are shear reinforcement, VUS. Okay, now this VUS can be provided in the form of either stirrups or bent up bars. Okay, there are two types of stirrups. One is, this is the vertical stirrups, then inclined stirrups. Okay, so the shear is rested by stirrups as well as if there is a bent up bars. The bent up bars, it goes something like that. This also comes under shear reinforcement. Okay, and stirrups and bent up bars. Okay, this is called it as the shear reinforcement, shear rested by shear reinforcement. Okay, therefore the shear rested by a section, total shear rested by a section is the shear rested by concrete plus shear rested by shear reinforcement. Okay, now we are going to see permissible shear stress in RCC. Permissible shear stress in RCC. Okay, it depends upon grade of concrete and percentage of tension steel used. The permissible shear stress, which is depends upon the grade of concrete and the percentage of tension steel which is used. Okay, now the permissible shear stress is tau c. Okay, tau c is the permissible shear stress, tau c, which was taken from IS 456 2000, corresponding a value of PT, percentage of tension reinforcement. This is percentage of tension reinforcement. Okay, this is the thing. Now the maximum shear resistance of concrete. Next point, maximum shear resistance of concrete. Maximum shear resistance of concrete, which can be calculated. The code says IS 456 2000. Okay, says tau C max is directly proportional to root of FCK, and the tau C max is equal to 0.63 root of FCK. So this is the value. This is very, very important. Tau C max. Okay. What is the reason for using this tau C max? The reason for using tau C max. Tau C max. First point, as load increases, on beam, tau V also increases. Tau V means VU divided by BD. Tau V also increases. That we know, right? As the load increases, tau V also increases. This tau V produces tension on one diagonal, and compression on another diagonal, Okay, now diagonal tension, one diagonal is subjected to tension, another diagonal is subjected to compression. We know that concrete is weak in tension, right? Therefore diagonal tension is here taken by shear reinforcement and diagonal compression. Diagonal compression is here taken by concrete. That means tau C max. So this is the reason we are using this tau C max. There are two stresses are coming. One is a diagonal tension, another one is diagonal compression. Okay, now what is the meaning? Suppose, let us take, let us take this point, okay, the support point. At the support, what is there? At the support, there was a stress, only the tension, shear stress, only the shear stress. So because of this shear stress, or I use the same notation which I used in the initial introduction part. This is the direction that I have used. Okay, now because of these two forces, this edge getting along it, this edge is getting along it, but this diagonal or this corner point is contracting. This is contracting. Therefore, this is the plane. Okay, this is the plane is subjected to failure. Along this plane, it is subjected to failure. Now see, this concrete element is now subjected to, there are two stresses. One is a diagonal tension. This diagonal tension which was taken by the shear reinforcement. So you have to put a shear reinforcement in order to take this diagonal tension. You have to put a shear reinforcement, something like that. Now, one more force is there, that is diagonal compression. This is the compression, this is the tension. Now this compression will be taken by concrete itself. That is tau c max. Okay. Now IS 456 says the tau c maximum, it depends upon only the grade of concrete. The grade of concrete. Okay. And tau c max equal to, we having seen 0.63 root of FCK. This is very, very important. Okay. You have to keep this in our mind. Now, what is the tau c max? Which was for different grades of concrete. Now, grade of concrete and tau c max. For a grade of concrete 15, if your value is 2.5. For 20 concrete 2.8. For 25 concrete 3.1. For 30 concrete 3.5. Then for 35 concrete 3.7. So these are the values. Okay, just to keep in your mind. Or else you have to plug the FCK value in that equation so that you will get a value. Okay, this values. So that is the thing. Okay. Now, the second point under this, suppose tau v is greater than tau c max. Tau v is greater than tau c max, then concrete under diagonal compression. Concrete under diagonal compression and gets crushed so that tau v should not be more than tau c max. If your tau v actual shear stress is greater than the maximum shear stress of the concrete, then what will happen? The concrete getting crushed. That means in this direction, the concrete will be crushed. Once the concrete is crushed, then only there is a shear reinforcement. Then the shear reinforcement couldn't able to take the shear force by itself. Okay, so therefore the entire section will be collapsed. So if this tau is greater than tau c max, then we have to redesign this section. Okay, redesign the section, that we will see. Next one is vertical stirrups. Vertical stirrups are preferable than inclined stirrups. Inclined stirrups, since it takes care of reversal of stresses. It take care of reversal of stresses. Okay, what is the meaning? See, let us take the same case, the pure shear stress, that is the support of the simply supported beam that we having seen in the introduction part. So this is the cube. Okay, this is the shear stress. This is the shear stress. Understood? Now we know that this corner getting elongated, this corner getting contracted. Okay, fine. Now see, this is the failure plane. This diagonal only getting failed because this direction is subjected to tension. The failures happen along this diagonal. Now, in order to arrest in the efficient way of using the stirrups is, actually I'm saying, actually if you use the perpendicular to this crack, then that is an efficient way to use the shear reinforcement. But generally we are not using something like that inclined manner, we are using the vertical manner. Why? That is a question. I'm saying the efficient way of using the shear reinforcement is perpendicular to the crack. That is the efficient way. But the problem is we are not using the inclined manner, we are using a vertical manner. What is the reason? What is the problem? The thing is, in some of the cases, there was a reversal stress. There was a reversal stress. When the reversal stress will come? Okay. So let me explain that. This is the inclined stirrups. Sorry. Because of the reversal stress. For example, there was a beam that you designed for a simply supported case. Simply supported beam. You design. This is the beam which was subjected to UTL. Therefore, this is the shear stress. This is the bending. Let us take this is a negative, this is the positive. For negative shear force, this is the, for example, this is the direction of the shear. Now what we are going to do, so we are going to lift this beam, we are going to lift this beam by using a crane, okay, to place somewhere, then what will happen? Now the same beam which was subjected to something like that deflection. This is a deflection. So initially it is subjected to a sagging moment, positive. Now this beam is subjected to a hogging moment, that is negative. And the shearing stress is reversed now. So because of this case, this is the shearing stress, this is positive and this is negative. Okay, let me draw somewhat big. Now the shearing stress is changed. This is positive. Initially it was negative. Now this is negative. Initially it was positive. And bending moment initially is what? Positive, but is negative. So because of this reason, now the shear stress is getting changed. This is the shearing stress acting at a support. So this is the positive. Therefore, reverse of the shear stress will be act. First initially left direction, this is the right direction. So everything is getting changed. Everything is getting changed. Understood? Now, which direction is subjected to tension? The direction, this is subjected to tension. Initially, what direction subjected to compression is finally subjected to tension, and vice versa. So this is initially is compression, sorry, tension. Now it is subjected to compression. Okay, in which diagonal now it is fail. So this is the diagonal, the failure is happened. Now think about it. If you use the inclined stirrups by considering the stress is happening like that, then the reverse condition, it won't stable. So everything gets collapsed. That means in this case you need to provide a shear reinforcement perpendicular to this. Then only it is stable. So from that we understood the shearing stress will be changed if there is a reversal stress or if there is a reverse bending moment. Then automatically the shearing stress also keep on changing. So when the shear stresses keep on changing, then the shear reinforcement also according to that we have to change. Otherwise, the system will be collapsed. That is the reason we have to use the vertical stirrups. If you use the vertical stirrups, then this will be holds good for tension as well as compression. Whatever may be the shear force, okay, somehow it will bear. Either it is failing in this diagonal, then also it will hold this portion and this portion, or if there is a failure which was happening in this diagonal, then also this vertical stirrups holds good this diagonal and this diagonal. So overall we can say the system will be stable. This is the reason we are using the vertical stirrups. I hope you understood. Okay, now next we are going to see the actual shear stress distribution. Actual shear stress distribution in RCC. In RCC. So this is the important examination question. Suppose there was a section in that somewhere here we are having a shear reinforcement. This is the shear reinforcement, is okay, and this is the neutral axis. This is the neutral axis, and this is the center point of the reinforcement, main reinforcement. The shearing stress is distribute parabolically up to the neutral axis. That means on the concrete side, the shearing stress is distributes parabolically, because we are assuming here is a homogeneous section. So this is the homogeneous section. Therefore, the shear stress is distributes parabolically. Then from neutral axis to center line of the reinforcement. Be careful, not up to the extreme fiber, up to the center line. Up to the center line of reinforcement, the shearing stress is constant. Okay, so we can write here actual shear stress distribute parabolically up to neutral axis in the concrete area, in the concrete portion, and constant from neutral axis to center of tension reinforcement. So this statement is very, very important. Now, but IS 456 2000, but shear stress distribution, okay, this is shear stress means tau v distribution as per IS 456 2000. As per IS 456 2000, the same section you have to take. Let me extend the neutral axis and the center of the reinforcement. This is the neutral axis, and this also same neutral axis. You know, this is the extreme point. This is up to here. Actual stress is parabolic with a rectangle, but IS 456 idealized this as average. Okay, average. IS 456 2000 assumed this is the tau v. This tau v is uniformly distributed. IS 456 2000 says consider the shear stress distribution is uniform, that is Vu divided by P into D. So this is the thing. Okay, this stress is called as nominal shear stress. Nominal stress. This one is called as nominal shear stress. Okay, now how to find the nominal shear stress for different size of the section. Okay, the first one is nominal I can write here itself. Nominal shear stress for prismatic beam and for non-prismatic beam. For prismatic beam, that means the section size is constant throughout the length. That is a prismatic section. In this case, shear stress at every cross section is Vu divided by B into D, and the cross section is B into D. But in the non-prismatic section, there are two ways to analyze. First one is the depth is increases towards the bending moment increases. See, this is the beam, non-prismatic beam. In this beam, the bending moment is maximum, or bending moment is increases leftward, moment is increases leftward, and depth also increases the moment direction. If the depth is increases towards the increment of moment direction, therefore tau v which is calculated, or tau v which is written as Vu minus ultimate moment divided by the depth into tan beta the whole divided by B into D. Next one is second case. This is the thing. Your depth is decreases in the direction of moment is increases. This is the another one. We know that moment is increases this direction M, but the depth is increases in the opposite manner D. Therefore, in this case, tau v is equal to Vu minus Mu plus this one divided by mu divided by d into tan beta, the whole divided by b into d. This is for prismatic tau b. This is for non-prismatic, which was says who? Which was says by IS 456 2000. So I have to keep this in my mind. Okay. Now we are going to see the critical section for shear stress. Okay. Critical section for shear stress. Critical section for shear stress. This is important. Okay. Generally, when a beam is subjected to a compressive force, then the critical section is taken as at a distance of d distance. Sorry. When a support is subjected to compression, then the critical section was taken as d distance from the face of the column. This is the critical section xx. Xx is equal to d. Okay. In this case, support subjected to compression. Okay. This is the first one. I can write when a support subjected to compressive force, then critical section for shear force is d distance from the face of column, or we can say support, from the face of column or from the support. And the second one is when a support is subjected to tension. For example, there's something like that L beam. There is a L beam, and because of this load, the L beam is now subjected to tension. Instead of subjecting compression, this is subjected to tension. For this case, the critical section was taken as the face of the column. This is the critical section. Okay, so we can write when a support subjected to tension force, then critical section for shear force is at the face of the column, or we can say support. So here the keyword is compressive force and tensile force. If a support is subjected to compressive force, then d distance from the face of the column is the critical section. When a support is subjected to tension, then at the face of the column, it is the critical section. Okay. So what is the meaning in this? Suppose there was a beam. and this is the support. This point is the center line of the support. This is the center line of the support. Okay, now the shearing force is subjected to UDL. Let us take a UDL. Okay, let us take a UDL. Then your shear force diagram will be considered. This is the shear force diagram. Okay, and moreover, as per assumption, the length, this is the length up to which your load is acting, W kilonewton per running meter, and this is the center point and the way which the shear force is acting. And the code says d distance from the face of the column is the critical section. So this is now the critical point. From the right support, this is the critical point. What it says, you have to use stirrups up to this critical support. Use closely. The stirrup shall be used closely up to the critical section, and from here itself also the stirrup shall be used very closely. Where the shear is maximum, shear force is maximum. After that, you can use the stirrups some higher spacing. Okay, we can use the stirrups somewhat higher spacing. This is, yes, okay, somewhat higher spacing. Why? This is not a critical section. The shear force anyhow less. Okay, but footnote, depends upon the shear force, the spacing will be there. Note, for a simply supported beam carries point load at the center, then stirrups spacing is constant along the length. Constant along the length. So that is a meaning simply supported beam subjected to stirrups, subjected to a point load at the center point W, and this is the center line of the support. Okay, then how the shearing stress distribution diagram? The shear stress or shear force distribution is something like that. Shear force, this is the shear force that we know, right? See, the throughout section, the magnitude of shear force is constant. Okay, for that you have to use the spacing of the stirrups constantly. But the code says the critical section is d distance. Critical section is d distance. Up to d distance you have to use closely spaced stirrups. Code says. But Actually, this kind of beam is subjected to equal shear force. Because of it is subjected to equal shear force throughout the section, you don't follow the code book. You have to follow the practical thing. So for that, in this case, you have to use uniform spacing of a stirrups. Okay, that's the thing. Now, next we are going to see design. So this is the final thing. So you have to be careful with this. I'm going to explain this with one example so that you'll get some more clarity on this shear design. Design of shear force. Design of shear in RCC. Design of shear in RCC. Okay, that's the first thing. In that, step number 1, point number 1, calculate design or factored or ultimate shear force at a critical section. So what is the meaning? Let us take a beam. This is the first step. Okay, let us take a beam. A simply supported beam subjected to UDL acting throughout the span. Okay, this is the center line of the support. This is also center line of the support. And this is the UDL. Let us take this UDL is equal to, for example, 100 kilonewton per running meter. Okay, 100 kilonewton per running meter. And the clear span of this is, let us take 10 meter or 10 meter. And what is the L effective? L effective, okay, which is equal to we can take minimum of, we know that this is LC, clear span plus effective depth, or we can say center to center distance of beam, or center to center distance of support. Center to center distance of support. So let us take the depth of the beam, effective depth, D is equal to 300. Let us consider. And this breadth is equal to, you have to take 200 of support. Breadth of the support is considered 200. Therefore, what is L effective? Minimum of LC is 10 plus 0.3 is equal to 10.3 meter. Center to center distance is 10.2 meter. Therefore, L effective, which is equal to, you got 10.2 meter. So this is the L effective that you got it. Okay, so L effective is over. Now, what is a shear force? How can you calculate? As per the code, this support is now subjected to compression. Therefore, the critical section for a shear force is this one. This is the shear force, critical section V. Shear force at the critical section, this distance is D. Okay, shear force at the critical section is equal to, we know that V is equal to, at the support, what is a value? This is a reaction. We have to calculate shear force at this point. Okay, that is, what is this reaction? W L effective, WL by 2, right? We know WL by 2 minus the downward force. What is the downward force? W into 0 point distance 0.1, that is 200 divided by 2 for this distance, plus the d distance. What is a d? 0.3. Okay, 0.3. 0.3. Now you have to substitute the values. 100. What is L effective? L effective is equal to 10.2 divided by 2 minus 100 into 0.4. So the answer for this is 10.2 into 100 divided by 2 minus, so answer is 470. So this is the answer, 470 kilo Newton. So this is the answer. B is 470 kilonewton at this point. Okay. So calculate the design or factored or ultimate shear force at a critical section. So factored shear force is what now? At a critical section. We know that you have to multiply with the 1.5. 1.5 into 470 is equal to, in the limit state I am saying, into 1.5 is equal to 705 kilonewton. This is the factor, meaning this is the working load now. Working load. Suppose if the load is a factor load, then you need not to substitute this 1.5, directly you have to take it. I hope you know. Okay, that this is the first thing, first step. And the step number two, calculate nominal shear stress. Nominal shear stress, that is tau V. Now what is a tau V? We know tau V is equal to V divided by B into D. V divided by B into D. Okay, then in that example, let me explain. The second point, right? The second point here. So let us consider the section is a rectangular section of having B is 200 and D is 300. Okay, let us take B is equal to 250 and this depth is equal to 500, for example. Then what is a tau V? Tau V is equal to, what is factor shear force? 705 into 10 raised to 3 divided by 250 into 500. So that 705 divided by 250 into 500. So the answer is tau V is equal to, approximately we are getting here 5.64 Newton per millimeter square. This is tau V. This is tau V that we are getting. What says this point? This is the thing. Here the condition is tau V shall be less than or is equal to tau C max. If tau V, then design is satisfactory. If tau V is greater than tau C max, then redesign the section. Then redesign the section. Okay. So for this case, your value is tau V is greater. Okay, for example, let us take M25 concrete. M25 is FCK. For M25 FCK, what is a tau C max? tau C max for M25 concrete is equal to approximately 2.8, right? 25, 3.1 megapascal. That means Newton per 3.1 Newton per millimeter square. That is your answer. Now in this case, tau V, the tau V is greater than tau C max. Then what we can do? Redesign. So in this case, redesign the section. So redesign the section means you have to increase the depth. Means increase the section means increase the depth. So let us take D is equal to 750 for example. Then tau V is equal to 705 into 10 raised to 3 divided by 250 into 750. So in this case, 7, okay, divided by 250 into 750. So answer is we are getting 3.76. So again it is not cold square. So let us take let me take this just for example. Okay, let me take 800. Then let me check. Yes, 250 into 800. 800, then 705 843 divided by 250 into 800. So again it is 3.5. It is not whole square. So let us take 900. So this is a trial and error process only. Let me check for a 900 section. Actually it's 900 and all. This is a deep beam, but just for example, it's a sake of understanding I am giving. Okay, so 705 divided by 250 into 900. So it's 3.1 now. What I can do, I can change the breadth and depth somehow. Okay, increase the depth and width. Somehow B is equal, let me take 350 and D is equal, let me take 750. Now let me check. 705 into 3 divided by 350 into 750. It's okay, fine. Now it's good. So if we take for this section 350 into 750, so you are getting 2.68 Newton per millimeter square. So this is the bottom point. Therefore tau V is now less than tau C max. That means 2.68, which is less than 3.1 for M25 concrete. Okay, now this is okay. This is the second point. Now second point is over. Now we are going to see third point. Suppose if tau V is less than tau C max, then we have to proceed further. So tau C max. Now the shear is taken by, first shear is taken by concrete. Next one is shear taken by shear reinforcement. Okay. Now we are going to see shear resistance by concrete. Here we are saying concrete, but this concrete means shear taken by uncracked section of concrete plus shear taken by interlocking of aggregate plus shear taken by double action of the tension steel. Okay, the combined together we are taking is a shear resisted by concrete, that is VC. Shear resisted by concrete, VC is equal to tau C into size of the section B into D. So this tau C, which was calculated from IS, calculated from IS 456 2000, corresponding to percentage of tension reinforcement, corresponding to tension reinforcement, RF. Okay, corresponding to tension reinforcement. So this is the shear resisted by concrete. Okay, and also we already seen this tau C is the permissible shear resistance, depends upon grade of concrete and percentage of tension reinforcement. Understood? This is the BC. Now one part is over, shear resisted by concrete. Then what is the balance? The shear resistance due to shear reinforcement, both one. So I can explain here in the third one. For example, the third statement is as per your tau C is equal, let us take 0.8 Newton per millimeter square, corresponding percentage of tension reinforcement that you are using. For example, this is not a true. For example, I am taking. For example, okay. This, now what is a VC? VC is equal to, excuse me, listen, this VC and this VC is not same. Actually, the combination of these three is the VC, okay, but IS 456 says, let us take the combination of these also as a considered as a shear resisted by concrete. But these two are not one and same. But IS 456 says you have to take it as the same. Combined together is VC. Okay, not only shear resisted by only concrete. Shear resisted by concrete means concrete, aggregate, and double action of bar all combined together, call it as VC. So we can take this is the small VC and that is a capital VC, so that you won't confuse. So this is small VC, this is a capital VC. Okay. Now VC is equal to 0.8. What is B into D? So let us take 0.8 into, already we having seen 350 into 750. Therefore shear resisted by concrete is 350 into 750 into 0.8. So approximately shear resisted by concrete is 210 Newton, which is equal to 210 kilonewton, that you are getting VC. Now some of the important points that you have to keep in your mind under this. What is what? So note, I'm writing here note. Under note point number 1. 1 minute. Note, we are going to see point number 1. So the first point is, we calculated tau C, right? If tau V is less than or is equal to tau C divided by 2. Okay, then no shear reinforcement is required in members of minor importance. So example, lintel. So if the shearing stress, nominal shearing stress on the beam, which is less than the shear resisted by concrete, permissible shear resisted by concrete divided by 2, then no shear reinforcement is required. But minimum shear reinforcement must be, shear reinforcement means here stirrups, must be provided or must be used. So this is the first point. Second point under this, and this was calculated by using a formula. This formula directly they will ask you in the examination. ASP divided by SV, which is greater than or is equal to 0.4 divided by 0.87 F. This is a point. Second point, if tau c by 2, the value is more than tau c by 2, tau a, but less than tau c, then minimum shear stress, minimum shear reinforcement, that is stirrups. Minimum shear reinforcement ought to be used in all types of members, and in this case also you have to use the minimum shear reinforcement ASP B into SV greater than 0.4 divided by 0.87 F. Okay, 0.87 F. That's the thing. Okay, now this is the note number 1 and note number 2. Note number 3. If tau c is less than tau b, that means the nominal shear stress is more than the permissible shear stress of concrete, but less than or is equal to tau c max. So in this case, the shear reinforcement, then the shear reinforcement shall be designed for a shear force equals to tau v minus tau c into BD. So okay, that is a fourth point, shear resistance. See, first point, second point, third point is over. Under third point there are 3 notes. So under third note, from the third note we are going to start the fourth point of design. So this third point comes under the, that is continuation of this third point comes in the fourth point of design. Okay, what is the fourth point of design? That is shear resisted by now. Shear resistance by shear reinforcement. We know that the shear reinforcement, there are 2 types of shear reinforcement. One is stirrups. There are 2 types of stirrups. First one is inclined, another one is vertical. Second one is bent up bars. And the fourth point is, it is denoted as VUS. So now the shear resisted by shear reinforcement VUS is equal to, we know the total shear force is what? V. We calculated, right? Already. Minus shear resisted by concrete, how much? 705 minus 210, which is equal to 705 minus 210, 495. You have to design for a force of 495. This is the shear resisted by shear reinforcement. Also, this can be, we can written as, what is V? V is corresponding, the stress corresponding to this V is nominal shear stress. Into BD, you will get a shear force. Minus, VC means what? Shear resisted by concrete into BD. If you simplify this, then you will get this formula. Tau V minus tau C into BD. But simply, you can take it as B minus VC. So that is enough. Okay. Now the shear resisted by concrete, we can write shear reinforcement is equal to V minus VC or tau V minus tau C into BD. This is the total shear resisted by shear reinforcement. Now we are going to see one by one. Bend up bars, how much takes? Okay, under this fourth point, we are going to take first one A. Shear resisted by bend up bars. Shear resisted by bend up bars. That also important. Let me explain this. Okay, shear resisted by bend up bars. That I can write shear resisted by bend up bars, VSB. Okay, VSB, the code says IS 456 2000 says VSB should not greater than 50% of total shear resistance of shear reinforcement, VES. Okay, should not greater than, you should not consider the bend up bar shear taking is more than 50% of total. Okay, the meaning is under this A point, total shear is 495, right? VUS is equal to 495 kilonewton. Then you have to design VSB, shear resisted by bend up bars ultimate. SB should not greater than 50% of 495. 495 into 0.5. 247. Therefore, 247.5 kilonewton. You have to design this shear reinforcement under bend up bars is maximum is 247.5. Suppose, okay, this is the condition, but the shear resisted by bend up bars as per the formula is equal to 0.87 Fy into ASB into sine alpha. That means this is the beam. Okay, beam, and there was a bend up bars. This is the bend up bars. So this is the theta. Okay, alpha. Okay, this is the alpha. Generally we will take this alpha varies from 45 degree to 60 degree, but the most efficient is 45 degree. Okay, sine alpha. In this case, VSB, which is less than 50% of VES, then okay. Suppose the calculator VSB, your calculator VSB is greater than 50% of VUS, then only take your capacity of bend of bars is more than 50%. Means the capacity of bend of bars is more than this 247.5, for example 300. If you get it 300, then you shouldn't take the 300, you have to take only 247.5 only. That is a code says. Then only take 50% of VUS. Okay, so this is the condition. Okay, so that is a first point under A point. Now B, shear rested by, this is the formula for limit state method. One more formula is there, BSB, which is equal to sigma ST, not sigma SB, sigma SB, ASB into sine alpha. This is for working stress method formula. Okay, now under this point number B, net force to be resisted by stirrups. So that is, now let us take VUS dash. I'm taking VUS dash. What is VUS dash? VUS dash, which is equal to, what is net force? Total V minus shear rested by concrete minus shear rested by bend of bars. What is shear rested by bend of bars? ESB. Meaning here B is equal to VUS dash, which is equal to, what we can write, 705 minus, how much this here, 210 minus VSB. For example, VSB is equal to 50%. Let us consider the maximum value, 247.5 kilonewton. So the value that you will get, 705, so which is equal to 705 minus 210 minus 247.5. 247, again you are getting 247.5 kilonewton. That is the thing. You understood, right? So this is the 247.5. You have to design the stirrups for this one. Now this is a shear reinforcement stirrups. Now this value will be designed for vertical stirrups, vertical stirrups, and inclined stirrups. Okay, so this is the final value, or we can say this one is finally. We can write this. What is V? Tau V into BD minus tau C into BD. That you know, right? What is VES? VSB is equal to 0.87 F1 into ASB into sine alpha for limit state method. In the similar manner, for working stress method also you can write, instead of 0.87 you are getting sigma SB. So the same thing will become instead of 0.87 F5, this sigma SB will become. So this is the net force resisted by stirrups. Okay, now C, this is the final design. Okay, now not a C, the spacing of stirrups. Now the shear reinforcement design, SB we will use, or you can write VUS dash, shear rested by only shear reinforcement, 0.87 Fy ASB into D the whole divided by VUS dash, the net shear force. Okay, so this is the formula. This is for uh, limit state method, and VUS dash is equal to sigma SB into ASB into D divided by VUS dash. This is for working stress method. Okay, so that is the thing. Now if we use these two are for vertical stirrups, now VUS dash is equal to 0.87 Fy ASV into D ASB into D into sine alpha plus cos alpha, sine alpha plus cos alpha the whole divided by VUS dash. This is for limit state method. Then VUS dash is equal to sigma SB ASB into D the whole divided by VUS dash into sine alpha plus cos alpha. This is for working stress method. These two for inclined stirrups. Okay, this is the B point. Okay, A point, B point. Now C point. Suppose, so here up to the bend up bars. Suppose if you are not using any bend up bars, so means 1 minute, 1 minute. Okay, if bent up bars are absent, if there is no bent up bars, then VUS shear rested by shear reinforcement is equal to total V minus VC, means tau V into BD minus tau C into BD, means tau V minus tau C into BD. This is VUS shear rested by stirrups, means in our example shear reinforcement, that is C. If no bent up shear reinforcement, if bent up bars are absent, then what is VUS? VUS equal to V minus VC, which is equal to 705 minus 210. So the answer for this is 705 minus 210, which is equal to 495 kilonewton. So this is the VUS. You got answer. You have to design for this. Okay, so this is the thing. Now what we can do, this is the VUS. Under this, okay, under this SB is equal to 0.87 Fy ASB divided by, in this formula VUS dash you put, but here VUS, entire value is taken by whom? Entire value is actually, sorry, this is the mistake. Okay, sorry to say, this is ESP, 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 ESP. If you want spacing, then this goes in this side. SB is equal to spacing of stirrups. Okay, now this is shear rested by only stirrups is SB. For limit state method, VUS is equal to for sigma SB ASB divided by SB for working stress method. These two are for vertical stirrups. Now VUS is equal to 0.87 FYASV into sin alpha plus cos alpha, sin alpha plus cos alpha, the whole divided by SB. Another one is VUS equal to sigma SB into ASB divided by SB into sin alpha plus cos alpha. I think one more quantity will come here, D into D into D into D into D. Okay, this is for limit state method, this is for working stress method. These two are for inclined stirrups. Okay, these two are inclined stirrups, and the VES is 495 as per our example. Simply you have to take it here. Okay, understood? That's a thing. So this is the now spacing. Okay, actual spacing. Check for spacing of stirrups. Spacing of stirrups, SB should not greater than D, should not greater than 0.75 D, should not greater than 300 mm, or should not greater than calculated value from SB equation. What is the meaning SB equation? So this is the SB equation. So take this SB here and keep it this VS here. So you will get SB. VS, you know, right? Okay, calculated. The VS is getting from these steps. So from that you will get a SB, that is a spacing of stirrups. Okay, that is a SB. Calculate a value from SB. Out of this, you have to adopt the lesser one, adopt, and this D only for inclined stirrups. If you use inclined stirrups, then use D, but if you use the vertical stirrups, then use 0.75 D. So anyhow the SB is based on 3 only. So either these three for vertical stirrups, and this one and these two are for inclined stirrups. Okay, this D or 300 or calculated value from SB equation, these three for inclined stirrups. In the vertical stirrups, 0.75 D, 300 mm are calculated value. These three are for vertical stirrups. Okay, these two last two are common for inclined and vertical stirrups. Okay, so that's the thing. So we having finished the shearing short note. Okay, so this is shearing design short note. So you have to go through some of the questions if you want. Okay, and whatever we have seen till now, that is enough for your state government examination. Just to watch it. Okay, thank you for everyone. We will see in the next class with some other topic. Okay, thank you.